And now let us give a couple of examples and non-examples for strictly convex spaces. First, in the product spaces. Depending on background, you might call this the Hilbert space. But for some people, Hilbert spaces are in the product spaces with the additional hypothesis that the space is separable. So it is safe to say, in particular for Hilbert spaces, are strictly convex. This is easy to check. I think you should be able to do it yourself. So you might want to pause this video and think about it on your own for a while, but I will give you the answer anyway. Suppose the normal space E is equipped with the inner product. We're going to check this with our definition number 3. Let xy be in E with x non-zero, y non-zero, and the norm of x plus y is equal to the norm of x plus the norm of y. So let us see what this condition tells us in terms of the inner product. From the inner product, let us look at the inner product of x plus y with itself. By the bilinearity of this real inner product, this will be the inner product of x with itself plus the inner product of y with itself plus the twice of inner product of x and y. And this thing, by the Cauchy-Schwarz inequality, is less than or equal to the norm of x times the norm of y. And we will write everything else as norms. And this is equal to the norm of x plus the norm of y squared. But the left-hand side, by our assumption, will be equal to this guy. So this is the square of the norm of x plus y, which is norm of x plus norm of y squared. So those two things are equal, so this inequality is actually an equality. Now recall that this inequality in Cauchy-Schwarz inequality becomes equality if and only if x is a positive scalar multiple of y. Here we are using that x and y are non-zero. So when this inequality becomes an equality, we must have x to be equal to c times y with some c greater than 0. And that is precisely what is needed for the definition number 3. So this verifies this. The inner product spaces are strictly convex. And as a concrete example, Euclidean spaces are inner product spaces, so they are strictly convex. So this is our first example. What other examples do you think we could study? What are some typical normed linear spaces that you think could be strictly convex or not strictly convex. Perhaps the most important norm spaces are LP spaces. So now let us study LP spaces. We'll first consider the case when P is strictly greater than 1 and strictly less than infinity. In this case, it turns out that they are strictly convex. Again, we're going to use the definition number 3 of strict convexity to check this. Let F and G be elements in the LP space with P strictly greater than 1 less than infinity, and assume they are non-zero. And the LP norm of F plus G we assume is equal to the norm of F plus the norm of G. And now recall, by Minkowski's inequality, we have the left-hand side is always less than or equal to the right-hand side. And the inequality becomes equality if and only if F is a positive multiple of G. Again, here we are using that F and G are non-zero. And the equality here should be considered as the essential equality, namely, it holds mu almost everywhere. So, by the definition number 3 of the strict convexity, LP spaces are strictly convex for P greater than 1 less than infinity. And this completes this example. Some of you may not remember the condition for the inequality in the Minkowski's inequality becoming equality. So let me remind you that this part can be obtained by looking at Folland's real analysis, second edition, page 182 to page 183, sections 6.2 and 6.3. Section 6.2 is about Horders inequality, and section 6.3 is about Minkowski's inequality. And in particular, you want to look at the proof of 6.3 for the case when P is greater than 1 less than infinity. Actually, this condition for the inequality becoming equality only holds for the case when P is greater than 1 less than infinity. When P is equal to 1 or infinity, things will get very complicated, as we will see in the following example, or non-example. Okay, so now let us look at the L1 space and L infinity space. And we will show that they are not strictly convex in general. This is essentially due to the fact that when P is equal to 1 or infinity, for the Minkowski's inequality becoming the equality, there's a much more complicated condition. However, to show that they are not necessarily strictly convex, it suffices for us to give some examples. Let us just look at the two-dimensional little LP spaces when p is equal to 1 or infinity. First, let us look at the two-dimensional little L1 space. In this space, let us look at the unit sphere. The unit sphere at the origin is a diamond. And clearly, each edge, which is a straight line, is contained in this unit sphere. So I should emphasize that we are using the definition number 2 of the strict convexity. Any unit sphere cannot contain a line segment in a strictly convex space. So, by the definition number 2, this little L1 is not a strictly convex space, since the unit sphere contains a line segment. And how about the L infinity space? So two-dimensional L infinity space has a unit sphere taking the form of a square. Again, this guy contains a line segment. So, again, by the definition number 2, little L infinity space is not a strictly convex space because the unit sphere contains a line segment. And this completes this non-example.